Good afternoon, all of you. In the previous class, we studied about free expansion and we derived some expressions with respect to reversible isothermal and irreversible isothermal changes. I hope all of you are clear with that. If not, please go back to that video and have a clear idea about it. So with that knowledge, we are continuing to the next part of thermodynamics, which is enthalpy. So enthalpy is a state function which does not depend upon heat, which tells us about the total heat content of a system. So enthalpy describes us about the total heat content or energy content of a system, and it is represented by the letter H. So with the help of our current knowledge, we are going to find out the expression for enthalpy. So when we move on, you make sure that you will write the expressions on time to the book so that you can connect it easily. So this is a known fact which we studied yesterday. So heat absorbed at constant volume is equal to the change in internal energy. From the equation of first law of thermodynamics, we came to a conclusion or an expression which is delta U is equal to QV. When volume was constant, the work term or the P delta V term got cancelled as we have delta V is equal to 0, and finally we got an expression which is delta U is equal to QV. It shows us that it is in the constant volume. So this is an expression which we derived yesterday. But in the real scenario, what we does is we don't keep the volume constant, or it is not very much possible to keep the constant volume without expansion or without compression. It is a tough process. So what we do is, for us to make constant, atmospheric pressure is an easy term. So to keep the atmospheric pressure constant, it is not a difficult thing because atmospheric pressure is almost constant all the time. So we prefer atmospheric pressure to be constant than that of volume. So this term becomes less important in a practical manner. Most of the chemical reactions, either it can be natural one or in the lab, most of the chemical reactions are carried out not at constant volume because it's a crucial process, but in flask or test tubes under constant atmospheric pressure. That is the term which we can easily make it constant. So that is the real scenario what we have. So we need to alter this equation. So for that, we are going back to our first equation, which is that of first law of thermodynamics. So first law of thermodynamics told us that delta U is equal to Q plus W. In that we substituted the W term with P delta V or minus P delta V. Hence the equation became delta U is equal to Q minus P delta V. All this we have discussed many times by now. So in this equation, when we kept constant volume, this term got cancelled and this became 0, and delta U was equal to QV, or a change in internal energy was depending only on the exchange of heat. So now what we are going to do is we are keeping the constant pressure and changing this equation to a form like this. So when volume was constant, delta U was equal to QV, which was on constant volume. Now we changed it to delta U is equal to QP, which indicates the heat exchange at constant pressure, minus the usual term which is P delta V. As this term is not 0, we can include that in the equation. So first thing we did with constant volume. By practical manner, we are doing it with constant pressure or constant atmospheric pressure. Hence the equation of first law of thermodynamics will become delta U is equal to QP minus P delta V. Now what we are going to do is we are going to elongate this term, or we are going to expand this term to this form. So delta U is equal to U2 minus U1, final term minus initial term. So that is a value of delta U, or change in internal energy. And one more term which we can improve is delta V. So V2 minus V1 is the value of delta V, as you all know. So that we substituted here. Hence now we are starting to rearrange this term. So U2 minus U1 is equal to Qp minus P delta V or P V2 minus V1. So that will become U2 minus U1 is equal to Qp minus, we multiplied this term with each other. So it became UpV2 plus PV1. So rearranging this whole equation, we get it into a form like this. So on rearranging, Qp we take to one side and other terms to another side. So hence we get it as U2 plus PV2 minus U1 plus PV1. We just arranged it in such a way that the second terms will come to one area and the other one term will come to one area. So the numbers or the initial terms are kept together and the final terms are kept together. That's what we done with the rearrangement. If you have any doubts about the rearrangement, please let me know in the group. So on rearranging, we got this equation, and this term, which is the sum of internal energy and that of work. In both the cases it is the same thing. In both the cases we can see sum of internal energy and that of work, or the sum of internal energy and that of product of pressure and volume. So this term is called the enthalpy. This new term, which we tell it as enthalpy. So we are going to define another thermodynamic function, which is the enthalpy, which tells us that enthalpy is equal to U plus PV. So this is the term which defines enthalpy, which is the sum of internal energy and sum of the product between pressure and volume. So this equation we are going to substitute in the previous equation which we discussed, which is Qp is equal to U plus U2 plus PV2 minus U1 plus PV1. So both the cases we can see U plus PV, which is equal to H. So that H we are going to substitute here. Hence the equation becomes Qp is equal to H2 minus H1, or the final stage enthalpy minus initial enthalpy. That will be equal to Qp, or change in heat with respect to constant pressure. And this will be equal to delta H. As it is final minus initial, it can be delta H. So Qp, or heat exchange at constant pressure, is equal to change in enthalpy. So enthalpy change is equal to change in heat energy. That's what we got from this expression. But there is a problem. So heat exchange is actually a path function, or it depends on the path which we have, and enthalpy is a state function. How is that possible? So Q is a path dependent function or a path function, and H is a state function. The answer for this we get from this expression, because when we write the equation for H or the enthalpy, we have U plus PV, and U, P and V are of state functions. So the internal energy, pressure and volume does not depend upon the path. So they are state functions. So the product of state function and another state function becomes state function only. It will not become a path function. So hence, when the pressure is constant, Q also becomes a state function, not a path function. So it depends upon U, P and V in this expression. So all of which are state functions. Hence, as it depends upon this, this also becomes a state function. Delta H is independent of the path, just now what we told. So hence, Qp is also independent of its path. Only when the pressure is constant, Q becomes a state function. So delta H is a positive for endothermic reaction which absorbs heat from the surrounding, and delta H or change in enthalpy is negative for exothermic reaction which evolve heat during the reaction. So to a system, when we provide heat, the heat energy will increase, hence the enthalpy will be more. Hence the final energy will be more than that of the initial energy, and hence H2 minus H1 will be a positive value. So you remember just this, when heat is supplied to the system or when it is an internal energy, delta H becomes a positive value. and when heat is removed from it, or when it is an exothermic process or heat is reduced, then delta H will be a negative value. So the reason behind this is in heat removal or exothermic process, initial temperature or initial enthalpy will be higher and final will be lesser. So final minus initial will become a negative value. So that is the reason why delta H is a negative value for exothermic reactions and it is a positive value for endothermic reactions. So this is the expression for enthalpy, but for finite changes we can alter this equation a little bit. So countable number of changes if they are happening, then we can write this equation like this. So delta H is equal to delta U plus the work term P delta V. Hence the sum of the internal energy change and that of work term will give us the change in enthalpy. Now at constant volume we have two equations here, delta U, the change in internal energy equation and change in enthalpy equation. In both these cases, if we keep the delta V is equal to 0 or constant volume if we are keeping, then both the equations will change slightly. So here we told delta H is equal to delta U plus P delta V. So when constant volume is kept, we can avoid this P delta V term or the work term there. Hence the expression will become like this. So delta U is equal to Q V, which means delta U or change in internal energy is equal to change in heat energy at constant volume, and delta H is equal to delta U. So when A is equal to B and C is equal to B, we can write this expression as A is equal to B is equal to C. Delta H is equal to delta U is equal to QV. So from this, if you see, you can write this equation delta H is equal to delta U and delta U is equal to QV. Hence we can write delta H is equal to delta U, which is also equal to QV. So if we try to state this equation or if we try to tell this equation as a statement, how it will be? At constant volume, enthalpy change of a system is equal to its change in internal energy, and that is equal to change in heat energy. That is a statement. So at constant volume, change in enthalpy of a system is equal to change in internal energy, which is equal to the change in heat energy. This expression is very important. So moving on, when heat is absorbed by the system at constant pressure, we are actually measuring changes in enthalpy. With this expression, we can tell this statement. So the expression tells us that change in enthalpy is equal to the heat change when pressure is constant, or at constant pressure, enthalpy change is equal to the heat change. But at constant volume, we wrote another equation, delta H is equal to delta U is equal to QV at constant volume. So when the volume is not changing, we can tell the enthalpy change is equal to internal energy change. So when volume is not changing, enthalpy change is equal to internal energy change. But if we consider solids, liquids and gases, the change in volume is not a big factor for solids and liquids as they are tightly packed. So solids and liquids, we don't have to compare much in case of expansion and compression as they are tightly packed. But in case of gases, elongation and compression is much more possible than that of solids and liquids. So we need to find another equation for enthalpy, and comparing delta H and delta U, we need to find another expression with respect to gases. So moving on, we will be considering ideal gas for that purpose. So we will take an ideal gas and we will find out the relation between delta H and delta U there. So when we consider ideal gas, we need to consider the ideal gas equation, which is PV is equal to nRT, where P is the pressure, V is the volume, N is the number of moles, R is a constant and T becomes a temperature. So we are considering a reaction where we get A gives B. So let's consider the reaction involving ideal gas. VA is the volume of reactant and VB is the volume of product. NA is the number of moles of reactant A and NB is the number of moles of product, all at constant pressure and temperature. So if we consider all this, we can write the ideal gas equation for reactant and that of product. How it will be? So PVA is equal to NaRT. This is the ideal gas equation with respect to reactant, and this PVB is equal to NBRT is with respect to product. So we wrote two expressions for the reactants and products, and now what we are going to do is we are going to subtract the equation B or equation A from equation B. So this we are subtracting, hence we get PVB minus PVA. So first the left hand side we are subtracting PVB minus PVA, which is equal to NBRT minus NART. And now we are going to do, we are going to take this P constant from here and NB or RT constant in this side. So this side we are going to take P as constant and this side we are going to take RT as constant. Hence we get the expression as P into VB minus VA is equal to NB minus NA into RT. So suddenly we will remember one thing, VB minus VA, what it actually is. It is delta V, right? In this NB minus NA, final minus initial, hence it is delta N. So that values we can substitute here. So we can write P delta V is equal to N delta N. So G we are representing that it is a gaseous form. So delta N into RT. So when we substitute this value to the enthalpy equation, which is this, delta H is equal to delta U plus P delta V. So in this P delta V we are substituting this value. Hence we can get a relation like this. So in this equation we are substituting the value of P delta V which we got from the ideal gas. So we got finally an expression for the relation between delta H and delta U with respect of ideal gas. So for an ideal gas, delta H is equal to, or change in enthalpy is equal to change in internal energy plus delta N RT. So this is an expression which gives us a relation between enthalpy change and change in internal energy with respect to an ideal gas. So with this we conclude our session now. We spoke about a lot of terms and equations in this class. So make sure you refer the textbook while preparing notes. Thank you.